Okay, let's get started. So for the next section, we're going to talk about how to use Python to access the data to science data, and also how to use cloud computing, also some deep learning stuff about how to do segmentation using some of those area imagery. And so we're going to use Python. So how many of you have used Python before? Okay, most of you. Don't worry, even if you don't, it's super easy. All the prerequisite is have internet access and how to click the buttons, and you'll be able to follow through. That's it. So, and hopefully after today, you'll be convinced to use why you want to use Python, to how to automate some of the stuff. And all the materials can be accessed by scanning the QR code here. Go to the same doc.js hub website. It should take you to this documentation website here. So this is the Python package that I created last year, and it's for use to do segmentation. So if you're working on some remote sensing data, you need to extract some information out of that. This can be helpful, and it's very easy to use. Like I said, just click the buttons, follow through, you'll be fine. On the left side here, there's a workshop. So you can click this one, IPPN 2024, and to get access to a notebook. It's pretty long document right now, but like I said, we're going to go through step by step, and you will have access to this one even after the workshop, so you can take a look at that even after. So actually we have two parts. The first part is using the segmentation. The second one is actually using Google Sensing. So there's, if you click the link here on the description here, click here, open in a new tab. I'm going to this is the second part of the workshop. We'll see how much we can cover, but the first one is like there's no prerequisite. All you need is just have a Google account. The second one does require a Google Sensing account. So if you don't have one, you might need to create one. I sent an email yesterday, I think 2 days ago, how to sign up one. Don't worry, if you don't have one, that's okay. You can still watch it. You can do it later. But it's very powerful. It's like you can do things in the cloud without, basically all you need is just a browser. That's it. You don't need a fancy computer. You don't need a server. You can do a lot of cool stuff. Again, go to this website. For those who are coming late, you can scan the QR code. You will be having access to the Jupyter notebook. And so are we ready?
Yes.
Yes. Already? Okay, cool. Just let's go to the first one. So we're going to use Google Colab. For those of you who have never used, how many of you have used Google Colab? Half and half. So Google Colab, how many of you have used Google Docs? I guess pretty 100%. So Google Docs is for writing text, right? Google Colab is for writing code, Python code. You can also use R. And it's very easy, it's free, and also have GPU. So we're going to use the free cloud computing resource to go through this notebook. And it also has GPU. So the Google Colab we're going to use is probably better than the configuration of your laptop. It's a lot more powerful than that. Again, go to this the website, and then on the left side, click this IPPN 2024, and just right-click, open these notebooks. So we're going to cover that. So we're going to primarily use the segment Geospatial, but it's also open source project. Upper right corner here, it can take you to this GitHub website. So if you're interested in learning about the source code, if you like to contribute, you're welcome to look at this one. So it's the one I created, but I also created many other packages. So if you go to the OpenGOS, Open Geospatial Solutions, you will take a look at all the packages that I created and maintain. So for today, we're going to cover three. The SamGeo for doing segmentation. Also the leaf map for doing visualization. Also created another one called Gmap is for doing cloud computing with Google Sensing. So we're going to cover these three most popular ones. And there's some other stuff in here. I don't have time to get into the details, but you're welcome to look at the organization. Welcome your contribution. Most of these I probably done 99% of the work, but we welcome contribution to the open source packages. So let's go back to this GitHub Colab here, and let me zoom in a little bit. So first step you need to do is to change the runtime. So I'll maybe change I would like to change to the light mode first for the time being. If you're using dark mode, you can continue to use that, but some of the the map interface will look a little bit weird. It's not fully supported dark mode yet, so I would suggest you just switch to the light mode for the time being. So just upper right corner here, click this button, and then if it's using the light mode, then you don't need to do anything. If using the dark mode, I would suggest switching to the light mode. That's it. And the next step is to change the runtime.
So if you need any help, I'll be around.
Mm-hmm. Yeah, just raise your hand. I can slow down. So for the runtime, change the runtime type. So if you click this one, because for this section we're going to use deep learning, machine learning. So you do need a GPU, otherwise it's going to be pretty slow. And so change the GPU. It's all free. So like I said, the GPU is 12 gigabyte. So it's better than most of your laptop configuration. So you do want to utilize this one. So change to the GPU and then just click save. Now we have this ready. And if you want, you can just click here, upper right corner, connect to T4. And then it should you are connecting to the Google server, and it's going to allocate the virtual computer, and then you can start doing something. So after it is connected, you should see a green check mark. And if you click this one, you're going to show you the RAM is 13 gigabyte RAM, 15 gigabyte GPU, and 112 gigabytes. So it's basically a virtual computer that we can use to do computation. Okay, are you all connected? See the green check mark? Okay, thanks to Google. I don't work for Google, but thanks to them for providing these free resources. It's very useful. Otherwise, you need to have a GPU. I don't think any of your computers, most of you don't have the GPU, so it's not possible for us to teach. So, and there are a couple things I want to go through here quickly. On the upper left corner here, you see this sandwich icon. So this one is basically the table of contents. So what we are doing here right now, we are seeing this Jupyter Notebook. Again, Jupyter Notebook is for doing computation. You can write text, you can write code on the same document. And it's very popular in the in the Python community for doing training, documentation, that kind of stuff. So if at any time, you need to just navigate through. So this is basically just like a table of content for you to navigate through. And so I'm going to close this most of the time. And after that, now we can get started. So we have all the settings. So the first step you need to do is to install all the packages. Google Colab has some pre-installed packages, but not everything that we're going to use have been pre-installed. So what you can do is to either just remove this hashtag at the beginning, or you just do Control slash on your computer, on your keyboard. Control slash. Or maybe let me turn on the keyboard so that you can see what I'm doing here. See my keyboard shortcut. Okay, is it turned on? Okay. So, oops. See, so sometimes if I have the keyboard shortcut, so you can see what kind of button did I press. So here, Control slash. Okay, turn this one on, and then just click this button. So this is all we need to do, is to click buttons. That's it. And just click it, run anyway, then you'll be able to follow through. So the nice thing about Jupyter Notebook is reproducible. So whatever I'm going to do here, what you see, you can get the same result. And this might take a minute or two, depends on the internet speed, but it should not be taking very long. And the longest one is this one, SAM2, the Segment Anything Model 2 for doing segmentation. It's basically compiling and then trying to install, so just be patient. Once you have this one, then we'll be ready to go. So basically we are setting up, installing the packages here. If you go up to the beginning, the leaf map for doing visualization, the segment and geospatial for doing segmentation, and the D2S for us to access the data from the data science platform. And
Question.
Yes?
So if you have a computer that has like a powerful GPU, you can install this package.
Yeah, you can install locally. Yeah.
Exactly the same way.
Yeah, it's the same thing. So if you have a powerful GPU, you're welcome to set it up on your local computer. And so if you go to the, let me show here the segment, not this one, the same Geo website here. You can actually install this on a local computer. So go to the installation. And this one shows you how to, if you are familiar with Conda, Mamba, you can install that. Or you can also, where you can go to my YouTube channel. I also have a lot of videos showing how to install stuff. So if you go to the Open Geospatial here, and yeah, I do have a YouTube channel that have tutorials. So if you just Google that, and I think I just recently have a video introducing how to install all kind of geospatial packages. For example, this one here, Geospatial. Anyway, we don't have time. You can watch it later. But there are all kind of ways you can install. But the easiest way, because not everyone knows Python, so the easiest way is just to use Google Colab. It's still installing? Okay. Maybe too many people are connecting to Google. They are complaining. Anyway, it should work. I just tested this morning. If it doesn't work, then it's going to be a disaster. Anyone finished already, or is it also stuck here? Okay, finally, it passed. So it's basically building all the dependencies. So deep learning stuff, the machine learning, sometimes some packages might take some time to install. But hopefully, once we get past this one, then we can start doing cool stuff. How to access the data, how to visualize the data. So basically what we are talking about here today, the analysis, we are going to teach you how to watch YouTube videos, but in geospatial, right? How to stream the data, how to visualize the data, how to run some analytics. For example, if you watch a movie, you want to show how long does that main character appear in that movie, right? In here, we are doing geospatial. We can count how many times, for example, how time series. We can access multi-temporal data, LiDAR data, all kind of data, and we can see that on the map interactively. Super easy to do. Okay, still, it takes a little bit longer than what I expected, but we'll be fine. Okay, just take some time. Anyone finish already this section? You're done? So basically, you're better than my computer. Yeah, I'm using maybe 6 years old computer to do that. So I'm also recording the video, so this might taking some resources, but everything is in the cloud, so it should not be too long. And if you already finished, you can just click the button. You can import the leaf map, see if it works or not. If it at the end, it might show some warning saying that you need to restart the section. You can click the button to restart the section. So if you see some red color warnings, you can just click that. Is it working?
Yes.
Okay. So everyone is working except mine. It should be done pretty quickly. Oh, okay. Almost. Okay, this is probably the last step. And by the way, so don't close the tab. If it's closed, everything will be gone. It might be there for a couple more seconds, but this is basically a virtual computer. And so make sure you click restart the section. There's some like version conflict, but don't worry, it's nothing serious. So once you restart the section, I usually just go here to clear all the outputs so that it's not taking too much space. Okay, are we ready? Okay, then just click this button, import diff map. So diff map is another package that I created for doing visualization of geospatial data. So vector data, raster data, there are a lot of data. If you're interested in learning more, just go to leafmap.org. There are tons of tutorial video and 2D, 3D mapping. So there are lots of novel examples. So you're welcome to try it out. What we're going to cover here today, a leaf map is probably only 0.01% of the functionality. So there are a lot of things in here that we'll not cover, but you're welcome to export it at your own time. And so I'm going to go back to normal here. So the first one is create a map. So just click this one. I can close this button and then just click the map. So what we are doing here, we are using leaf map to create an interactive map. So can you see the map? Okay, you see, super easy, 2 lines of code, nothing fancy. It's just using the OpenStreetMap base map in here, so you can zoom in and can zoom out. And this is how you can create map using Python and Jupyter Notebook. And by default, it's showing the global map, but you can customize it. For example, different location, zoom level. I don't know why it keeps showing this one. Anyway, so right now, for example, we create a map center around the US, latitude and longitude. So the center is latitude, longitude, so 40-degree latitude, negative 100, basically the waist, negative 100, zoom level 4. So the larger the zoom level, the more zoom in. So you can change the zoom level, for example, to maybe 14. You can change it, so you can customize it. It's all very flexible. And after that, you can add some base map. So you can add, for example, Esri base map. This is so annoying. It didn't show in the past, but okay, this is better. So, and you can zoom in, you can zoom out. So right now we're adding the Esri wall imagery base map. So also, upper right corner here, there's a button. So if you click the button, upper right, it's going to show you all the toolbars. And you can click this one. You can actually turn the layer on and off. Eh? I think something is a little bit interesting. It's not. Okay, this might be a bug. Anyway, so just click this one. You can add all kind of data layer, all kind of base map data layer to the map. So there are hundreds of base map available on the internet. And OpenStreetMap, for example, the Google base map. And probably the easiest way would be just this one. Execute this code block, add base map GUI. So in that way, you can switch base map in here. So you don't have to remember the name. For example, you can just click this one, Google Satellite. And you see you have the Google Satellite. You can choose whatever map you like. For example, they say the ESA global land cover dataset, for example. So there are a lot of data layer available. You can click the button here. You can turn the layer on and off. See that? So you can also change the opacity. You can zoom to any location you like. So this is the web services. Just like you're looking at Google Map, right? There are tons of maps, and you can see different land cover here, agriculture, and you can take a look at what's behind the satellite imagery. So this is just the land cover data. And this is just a simple way of creating interactive map using Python, right? Leave map.map, and then that's it. And then you can add base map, you can customize how it looks. Next, let's talk about how we can access the D2S. So Jinha talked about the using the D2S platform, but everything we can access programmatically using Python. And this actually is better than for teaching because we use the same source code, so you're going to get the same result. Otherwise, sometimes it's difficult to keep up with the every step. So for this one, what you want to do here is to change this one to your own account. So you just signed up this morning. So change this one to your own account, okay? So I'm going to change it to my account. Okay, and then just run this one. It should probably ask you to enter your password. And so I'm going to enter my password. Oops. I probably need to, oops. I need to turn this one off so that you don't see my password. There should be an option for me to, 1 second. Oops. Preference, oh, here. I think this keyboard mode. Anyway, I think I don't need it. So let me just turn this one off. So it's not showing me anything. Okay. So I'm going to enter. Hopefully it works. Okay. So if you see the green check mark, that if you don't see any error message, that means you are authenticated. So we get the API key. So if you don't, you need to generate the API key from oh no, you don't need to generate it from the website, right? You can do it from here. And then run this one. Hopefully no error. If you run into error, let me know. Otherwise, you cannot do anything. Okay, you won't be able to access the data. Are we good so far? Any problems? Okay. So yeah, just change this one to your email, and then run it. Enter your password. Then you should have access. Are we all good? Okay, then just click the buttons. You can continue, you can try things out. So it doesn't really, you're going to see a lot of source code, but it's mostly very easy to understand. So earlier when Jinha introduced the Data to Science platform, right, you remember you create a new flight create a new project, and then each project has different flights, right? So what we're doing here is to see what project you have access to. Your interface look different than mine. Probably have 2 to 3 projects listed right now, right? Can you see any output here? Right, so the sample workshop project you should have access to. And so we print out all the project. This is the project that I have access to. And you can also filter the project by title. So from this one here, C3 Ultra title here. So we're gonna use this project to do the demonstration. So this one just shows you all the projects that contain this search keywords. After that, because we only have a list, right, we're going to just access the first project. So basically what we're telling the program is that I want to use this project, just run it. Once you have the project, then we can access some of the data. For example, the project boundary, right? The one that you click the checkbox, you can see the bounding box of the project. And this one just shows you all the coordinates. Basically the GeoJSON file that we uploaded from the project. And for each project, you can have different flights, right? You can have RGB, you can have multispectral, you can have LiDAR. So this one here is to get all the flights, right? So for this particular one that we looked at earlier, one is from June 9, the other one is December 15. So RGB, and there's some metadata information in here. You don't have to worry too much right now. We can just continue. So if you have many flights, right now this project only has 2, but if you have like 10, 20, probably you also need to do the filter. So depends on, you might have like early season, mid-season, late season, so you can actually filter by different months. So we have all these flights, for example, okay, I only want the flight in June, okay? So you can specify the start day, June 1st, and the end day, you can customize it. Then, okay, we're accessing right now, filtering the data to just the first flight, right? And after that, you can use the flight. So again, this is some kind of a little bit repeated, but you can apply to other projects that has a lot more flights. I'm just showing you how to access the data programmatically. And once you have the flight, then you can have access to the data products. Maybe let me just open this one so that you can actually see d2s.org. So you can see basically what we are doing using the interface, but right now we are doing that programmatically. So I'm just here. Oops, I think I changed my password. Yep, again. So I'm not going to, let me just turn this one off. All right. So what we're doing here is we are doing this project in here, right? So this one has, oh no. Oh, the workshop one, okay. Workshop, I believe it's this one, right? So basically we are accessing this project. This project has 2 flights, and so right now we are accessing the data products, right? So you can click, you can see you have 3 data products in here. So it will be this one. Oh no, not the same one, sorry, this one. So basically right now we are accessing this one programmatically, this project. So it has the DSM, the CHM, and also the mosaic, right? So you can click here. Earlier, right, you can see the data set. But right now we are accessing this through the Python API here. And you can filter by also. For example, I just want to look at the also imagery. I just clicked earlier, but now I'm accessing this data. Just click this one, then we are visualizing this one on the map. So we're actually pointing to the data, so it should zoom in automatically to the area, and then it should show you the imagery. Okay. All right. So right now, this is what we're seeing here. It's exactly the same that you're seeing on the platform using this one. The advantage is that right now is Python, so you can actually integrate multiple data layers, so you can add as many data layers as you want. And also you can, upper right corner here, you can turn the layer on and off, for example. And you can also turn on the base map, Google satellite base map. You can change the opacity, you can take a look at the differences. So the Google base map, I don't know the exact day that was acquired, but you can certainly see. It's loading up, but certainly this is wrong imagery. This is 1 centimeter So it's much better than the Google-based map. So you can actually, it might take some time to load up because we are all accessing the server. But you see, this is from Google, and this is from our Jung imagery that we were seeing. Right? So it's super cool. So now you can load the data, visualize that in the Jupyter Notebook. And similarly, we can visualize the DSM, right? So in the D2S, we can go to the DSM in here. If you click, right, you can load the DSM in here. We can do the same thing. So you can get access to the DSM data products, filter the data, and then we can add the data layer to the map. So it's called add code layer. So cloud optimized GeoTIFF data layer. Is it coming up? I think some Google stuff is a little bit. If it doesn't come up, you can create a new code block. Click the add code button, and then you can just type M, the lowercase m. Basically, is the map. So you can display it again. Now you see here. There's something. Oh, okay. It comes up. It's just not instant. So you can see this one right now. This is the DSM again. It's loading the tile. So it depends on internet speeds. It might take a couple seconds to load the entire map. So this is the DSM. You can also display the CSM and other stuff. Yes?
Sorry, every time I try to load,
Uh-huh.
I get an error, band descriptions.
Band description? Anyone get the same error message? Are you running it locally, or you're running using Google Colab?
No, it's this one.
And you can also click this one, the statistics. So this is similar to what you see from the platform. You can see some of the basic descriptive statistical information about the data. And we can also add a color map. The color map, oops. Oh, I see. Huh. So probably some of the packages that are Google Colab updated, so it's breaking some of the stuff. This is, don't worry, this is non-essential, so don't worry too much. If it doesn't work, this code block, we can skip it. It's just for visualization, so it doesn't really affect the functionality. So let me skip this one, and we can add a GeoJSON and see if it works here. Okay, so if you add a GeoJSON, the yellow one is the one for the project boundary, so I can turn off maybe the DSM, so you can see better. So when I hover my mouse, you should see the yellow rectangle. This is basically the project boundary from here. Oh, the tree boundary, but it is this white one here showing you. But we can also add the tree boundary if you want to. So you can continue to click the tree boundary and then add the tree boundary back to the map. So now we should have both. So if we zoom in, let me close this one. So can you see this tree boundary? Yes? So again, if this code block doesn't work, this is fine, don't worry too much. You can just Control/ to comment it out. And okay, any other issues? So this is for the June 9th. So basically the summer season. But we can also get the other one, right? So from this project we have also the December 15 one. So we have basically two flights. So the next one we're going to look at the December 15 flights. And you can do the same thing. So I'm also filtering the data here using the start and the end date. And so we are getting the December 15. And the next code block, this is one allows you to compare the data side by side. So if you click this section, then you should create a map with a split map. So similar to what we did earlier using the data to science platform, but now we're doing it in Python. So again, the internet is a little bit slow, but you can zoom in. You can see this. So the one on the left is June. Or lower left corner here, you should see the label. So we're adding the label here. The other one is December. So we are comparing these two time periods here. Let me zoom out a little bit. Does it work on your computer? This one? Compare to also images. So you can zoom in, you can see the details in here. The one in December have some, like, I think depends on the angle. So that you can see some tree shadows here. The one June 1, the June 9th, that one is little bit, it looks a little bit better. So the shadow sometimes has some challenges for doing segmentation. We'll show you later, but so I'm going to use the example from the left side for doing segmentation. Okay, any issues? So this is basically similar to what you use the web interface to see the data, but right now we are doing it programmatically. So you have precise control about what data do you want, how to customize the visualization, things like that. And the next step, we are actually trying to really get the data out so we can start running some data analysis. So here, we are going to use the package called Royal X-Array. So you can just import it, and then we're going to, oops. So basically, I think Google Colab just updated something last night or this morning. It was working fine yesterday. So I might need to reinstall the package. Are you getting the same error message here? Yes? So let's fix it. Yeah, this is like the danger of doing code live demo. You're going to run into this issue, so you have to fix. The problem is that the NumPy, they updated to 2.0, I think a month or two ago, and then some of the packages are not quite compatible. So
I didn't get the same error.
You didn't get the error?
I think that probably when you pick the runtime, make sure that you pick Python 3.
Yeah, it's Python 3, so it should be Python 3. So let me go. Let's go back to the beginning. Let's fix it. It should be fine. I think just the NumPy version is having the issues. So let me go here, add a new code block here, and then just type %sign pip install NumPy equal to 1.26.4. I think that's the one that's the late, the 1.0 version that actually works. So let me see if it works. So install this one. NumPy equal 1. Okay. So go to the beginning of the notebook and then just create this, add a new code block, and then type this one. And after that, runtime, restart runtime. Restart section. Restart section. So hopefully it works. If it doesn't, then we find another way to fix it. Okay? And after that, you need to re-import the packages. For example, just import leafmap again. And see if we can create a map. Alright. And so what you need to do here is to click this one and then go to the log into D2S again because we restart a section. So you need to log in again. So sorry about that. It's annoying. Okay. Log into your D2S again, and then just run load section again. It should work fine. and we can see if it works now. Flight, get the flight. Yeah, just run the same code blocks again and see if we can load the data, and hopefully we'll be able to read the data from D2S. DSM, this one. Okay, so we can see the data, statistics. Maybe now I can try this one. It may work. Okay, perfect. Yeah, it's just a NumPy issue. So now actually you can see this, the color map, the color bar that I just added. Now it works. So what I need, I will go back to change the notebook so that we need to pin the NumPy version. And then the project boundary, get the map, add the tree boundary. So you should have all the data available now. And then this one, compare side by side. Okay, so let's try this one again. I'm nervous. Okay, perfect. So now it works. So basically it's NumPy. The NumPy package version issue. So try this one. If you don't see any error messages, you are good to go. And then we can use this one to read the data. So we are not utilizing GPU, but yeah, pretty soon we use the GPU. So we're using the X-array, RIO X-array to load the data. So basically, all the data from the D2S is called Cloud Optimized GeoTIFF. So its data is over there, but if we need to run some analysis, we need to pull the data. Kind of like you're seeing all the Google Earth imagery, right? It's for viewing only. You cannot run any analysis on that. If you need to run analysis, you need to get the original data. So right now, we are trying to access to the original data here. So this one shows you this imagery has 4 bands, and how many rows, how many columns, okay? So it's a pretty big imagery, and this the data set itself is 1 centimeter resolution, so it's super high resolution, and you need a large GPU to do the data processing. So for this example demo, we're just going to just get a small subset data set out. So what we're going to show you is, first let's look at the imagery. So this is from June 2026, right? The one that we just visualized earlier, but we can create a new map again here just to, where is it? It might take some time to load up. And so leaf map allows you to draw a rectangle so you can clip the imagery on the fly, but we're just going to use this same bounding box, just run this one, and then add the bounding box to the map. Huh? Oh, it's here, sorry. It's pretty tiny, but so basically we're loading this imagery, and then we're adding this bounding box. What we want is we want to clip this imagery to a smaller area. Can you see this one? Yes? And then what we are using, we need to clip the imagery. So we are basically running these two code blocks to make sure your bounding box has the same coordinates, the same projection as the Jung imagery. So the Jung imagery data is in this UTM projection, and we are use this bounding box also projecting them to the same projection, so that the coordinates are in the same unit. And after that, we can do the projection, So this is one is going to take the most time. So click this one. It might take a minute or two. I think like imagery is like 400 megabytes. So basically, it's going to the D2S server to get the data, read the data, download the data, and then resample from 1 centimeter to 10 centimeter because we don't have the GPU big enough to handle the 1 centimeter. But the 10 centimeter is fine because it's going to downsample. So from 1 centimeter to 10 centimeter. So think about the file size decrease. How many times is going to be decreased if you change from 1 centimeter to 10 centimeter? It's 100 times, right? So because it's a pixel, so previously you have 1 pixel. Right now 1 pixel is equal to 100 pixel because 10 centimeter, right, width and height. So the file size is going to decrease 100 times. So from like 400 megabyte to just 4 megabyte. So it's much smaller. And this is the taking some time, so it depends on how many people are accessing the server. So
This is for visualization, right? The projection of the resolution is for visualization, or?
no, this one is we're going to do analysis. For visualization here, this one is 1 centimeter. This is the original. And the nice thing about this is because when you zoom in, it's going to get the tile. So this is called dynamic tiling. So you can see the highest resolution possible. But the reason that right now is 1 centimeter, everything works perfectly because we are only seeing a small subset of the data set. So you think about Google Earth. The entire globe, the imagery is like thousands terabytes. But because when you zoom in, the area becomes small and the file size is small. When you zoom out, the resolution is resample. So the resolution is small, the area is large, but the data that you are transferring is still pretty small. So this is why we can visualize the data in the original 1 centimeter. But when we are really running analysis, we want to resample that so that it's much smaller. So right now you see here, 1,960 compared to the previous one is 16,000. So we are just getting a small sample. Basically the coarse resolution one so that we can run the analysis on that. Okay, so are you done with this step? So this one, the sample here, this is 0.1 meter. So it's 10 centimeter, right? So the original one is 1 centimeter. So it's very, very high resolution. So this is the one we're going to work with. And we can also clip the data. So because we just want the area, we just want to run analysis within these bounding boxes, the entire image is much larger. So we're just going to focus on these small areas. So that's why we are getting this, the bounding box in here to clip this one to the bounding box we want. And then we're just going to select the first 3 bands. So we're just going to select the RGB. So this one, the last band is just the mask. So we don't need that. So we're getting the data, basically we're resampling the data, and then we are downloading the data, get the 3 bands, and then, so now we can visualize the data. So this code block here, right now what we're doing is actually, now the data is no longer on the D2S. The data right now is locally. And not really locally, it's still in the memory. So you will see here, right now we have access to this data, so you can see we have clipped the data to the boundary that we want. You can also, you can hover your mouse, you can see the lower right corner here, this dialog is changing. So basically you are seeing all the tree, the boundary. If you don't need it, you can close it. And so, oops, I'm gonna move a little bit here. The tree boundary is overwhelming, you can turn it off. So what we just did is we get the data 1 centimeter from D2S, resample to 10 centimeter, and then downloaded it, and then visualize now on the map. So that's it. So this is how we did it programmatically. You can use it to do other data set if you want to. Okay? So this is how we are doing, and right now it's basically just prepare the data ready to do deep learning. Okay? Can you all see this map now? All right. So now we are really going to use GPU. So earlier Google Colab is complaining that we are not using GPU because it's a lot of money to run the GPU. So right now you see it's 0 gigabyte. We're not utilizing it yet. But very soon, oops, what is runtime? Okay. So probably I'm not using it. They recycle the GPU. Anyway, so let me reconnect. So we should be good now. So what you need to do is just to run this one. I'm not sure if I need to rerun the previous code or not. Sometimes it gets disconnected. All the things in the memory are gone, so we might not be able to use that. But is it still works? Yeah, it might still work. We can try. So just click this one, same geo. So we're going to use the segment anything model 2. So this is the model, so-called the foundation model released by Facebook that allows you to do segmentation on imagery, and is trained on like regular photos, not trained on geospatial data, and I kind of adapt the model to make it applicable to geospatial data, set imagery, Jung imagery. So So we're going to load this one, load this model, and this is where right now it's going to download the model. So if you click this one, you can basically monitor the GPU usage. Right now it's downloading the model. So kind of like ChatGPT. We are downloading the ChatGPT model, and then we start doing the inferencing. So right now it's just downloading the file. So this one is 898 megabyte. And once it's downloaded, it's going to load into the GPU. Then you should see a spike here on the GPU usage. Almost done. All right. So if you see it's spinning, and on the right here, okay, right now it's only a tiny. So you see 1 gigabyte. So because this model is 898 megabytes, so it's loading it to the GPU, so it's going to be much faster. Then you can just click this one. So I'm not sure if it works or not, because it restart my kernel. So if it doesn't, then we need to. Okay, perfect. It works fine. So it's on the right here. You see the GPU 3.9 gigabytes, so it still works. Now we can do the save the mask. So I can close this one right now. Show the mask. All right. So you see this one? So this is from this imagery. So what we are doing is that I want to do the segmentation. I want to segment each tree from this imagery. And this is so-called the foundation model that you don't need the training, right? So if you have done remote sensing before, if you need to segment the object, you need to provide the training data, you need to train your model. We don't do any training here. We just use the so-called the foundation model. Just like ChatGPT can help you answer any questions. ChatGPT doesn't have to know you, right? You can just enter the information and then you spit out some output. This is the same idea. So right now, I give you the imagery and then ask you, okay, segment all the objects within this imagery. And just 2 lines of code, you see, now we have this imagery. And you see it's like the gray color. So you have dark color, you have white color. So the color, basically each color represents a unique ID. And it's increasing, so the brighter the color, the larger the area of the object. Yes?
How flexible is the generalization capacity of the model? So if I change this field for...
Yeah, it doesn't matter. It can be anything.
For another crop?
Yeah, it should work. And this is why it's called segment anything. You give me an imagery, I segment it for you. And actually, behind the scene, it actually provides 3 outputs. We are just picking the first one with the highest probability. But you can, for example, sometimes it can be very ambiguous. For example, you can put a point. This is called automatic segmentation, but later I'll show you some more interactive way how to do segmentation. But you see here, just 3 lines of code, initialize the model, and then just say generate. Basically, you're going to okay, ChatGPT, answer my question, show me the output, and that's it. And now you have this data in here. So this is just a grayscale imagery. I'll show you the output in here. You can also show a mask, but mask basically shows you, give you a random color. And the color doesn't mean anything, it's just random. So it doesn't know the species. So if you have an imagery that have different tree species or agricultural crops, it will not, the segmentation model does have no idea about what it is. It just knows it's an object. So it's kind of mimic human vision. So for example, right now, I take a photo of the classroom in here, put it into the model, it will extract each of you. But if they don't know your name, they don't know where you're from, they don't know your race and ethnicity. But we identify the object because it's based on basically the region, the similar pattern. Okay, so this is just the simple way of doing the segmentation. And then you can actually overlay the segmentation result on top of the set imagery. And clearly you see here, you have some like nice random color, but you see it means a lot of loss. And this is where you need some fine tuning, because even though it's called segment anything model, it can segment anything, but sometimes it can segment some garbage, like garbage in, garbage out. But this is why you need some fine tuning. It's not going to work in all cases. Just like you ask ChatGPT, sometimes the result is not right. Sometimes it's like hallucinating, give you some like not so incorrect result. This is perfectly normal. So don't panic if you see the result. It doesn't look good. But if you see from here, we don't train the model. If you need to read to train the model, you need to have the training data, you need to have the label. It's going to take you hours before you can actually do some segmentation like this. What we're doing here, maybe a minute, you get the result. It doesn't look good, and we fine tune it. So next, we want to show you how to fine tune the result. But before that, you can actually have this one, so you can have some visualization, you can do the slider. But actually, you can add everything back to the map to do visualization. So this one just shows you here something like this. Pretty cool, right? Just one line of code. So we are loading the original imagery, and we also loading the segmentation mask just to compare the result side by side. Again, it's not perfect. It's okay. We are going to improve a little bit. So later you can see a much better result depends on our input data. And so once you have this, we can actually add this one back to the interactive map. Again, let me move this one back in here. So again, it's a little bit interesting. So you can see the color in here, as you can see the tree boundary. And you can also see the mask. I think something is wrong because it restarted the kernel earlier. So that's why it's not. Or I can do it in here. I can add you can create a new map or equal to leaf map.map. If you just want to show the mask, then you can also do it this way. Hopefully it works. Okay. So now I don't have the imagery. So what I can do is to, anyway, I need to rerun the code block above. But you get the idea. So this is how you can see the base map, and I can maybe, how about this? m.add base map hybrid. So I'm going to just use the Google base map for the time being, and take a look. Right? And there's some offset. I think the Google base map have some offset, so you don't see them align perfectly well. And this is very high resolution. So it depends on the base map we're using. But if you load the also one, let me go back to here. This one. So the add imagery. So this is the one. I think should be this one. Did I download it already? Oh, okay, it's actually already here. So all I need is just copy this one, or maybe just this one. Then it should work. Okay, so now much better, right? So I load the original 10 centimeter resolution. Then we download it from D2S. And let me turn this one off. You can actually see this. Right? That's pretty well. It's not perfect. You're going to miss a lot of those. We're going to fine tune it. But for those that were detected, not bad, right? It aligns pretty much very well with the real tree objects. And depends on how complicated the imagery, sometimes it will not give you good results. It's also perfectly fine because the model itself is not trained on this data set. The model itself is not trained on satellite data, remote sensing data, but it has so-called transferability that behind the scene, it's basically just identify similar patterns. If they're similar, they're being grouped at the same object. And if they're very homogeneous, you're going to get everything will be just one big project. But in this case here, it's pretty obvious because you have all the trees. They are kind of separated, so it's very easy to identify the object. And besides that, you can also convert it to vector data. So I can just run this one to convert the segmentation result to vector data. So and then you can add the vector data back to the map. So now you see the yellow color, pretty good, right? So if you're dealing with you are using with desktop.js, you can also later I'll show you how to calculate all the information within each polygon. I actually just last night I implemented some additional function that allows you to calculate the area or the geometry and then some like geometric properties. I didn't show it in the notebook because I didn't have time to finish that, but I will show you later how to access this, right? So now we have this pretty basic, simple one, classification result. Yeah, that's what we're going to do in the next step. Yeah, so right now, because it means a lot of trees, it doesn't look good. So the next step here is that these are all the parameters you can customize, okay? And so earlier we didn't customize anything. So what we are doing here, actually I only changed these two parameters. So earlier I think the default one is 32 and 64. So what it's doing, how it's doing the segmentation is giving an imagery, it's going to place a grid equally spacing points like 32, and then how many rows, how many columns, and then for each point, it's basically like doing like region growing to find the similar pixels. So right now we are placing more points. So in that way, you are getting like better results. So let's try it out. So just run this one. Again, it's going to reload the model, reinitialize the model, and okay, it's done. Then we're going to regenerate the result, and so this time should be much better. So the generation, this is the one taking the longest time, and this is the one that's really using the GPU. So you should be seeing the spike, the usage in the GPU. So if you have a really large imagery, if it is more than what is available, you will not be able to do that. Then you need to choose a smaller one or resample the data to a much coarser resolution so that we'll be able to use that. And hopefully it works. I've tested it yesterday. It works fine. So when you start seeing the yellow color, that means you are close to the limit. So that means a good sign that it may or may not work. If under the green is green color, then it's usually it should be fine. And certainly this one is taking longer because we're using more points. So basically, kind of like I'm trying to do the segmentation. So you need basically some starting point to identify objects. And the more points you have, the more object you're going to identify, the more computation you're going to use. And this is taking, I think, more than double of the time. But okay, 12.4 gigabyte right now. I'm getting nervous. If it's getting to the red color, then it might be problematic. But hopefully it works in our example here. And you can see the output in here. Right now, compare this one to the previous one. You will see so much more detail, right? Compared to this one. A lot of missing trees. This one pretty much captures all the trees. But the downside, you're going to see some of those like artifacts in the background. Like those elongated, those are not really trees. Like I said, the model itself doesn't know it's a tree, it's the ground, it's anything. It's just an object. So it's going to give you segment everything, every pixel in that imagery into individual objects. And then you can do some like fine tuning. You can extract the information you want. There are some other, if you go to the SamGeo website. So for this workshop, we only cover like the automatic segmentation, but there also you can do interactive segmentation. So this one shows you, for example, here I can select points on the map, and then you can select the foreground points, background points. It will extract that object for you interactively. So similarly for the agriculture, you can select a tree. It will extract the tree for you interactively. For example, you can also do buildings, something like that. Let me refresh so you can see the example. Again, I don't have time to cover that. You're welcome to explore this one after the workshop. So allows you to load any imagery, and then all you need to just click the button. I want this one. So in remote sensing, this is kind of like called supervised classification. The one that I showed you earlier is called unsupervised. I didn't provide anything. I just give you an imagery. You segment that for me. You can do interactive segmentation. I give you a couple points. And then it's going to segment, for example, I'm going to extract the buildings. I place points on a couple buildings. And I didn't place points on all the buildings. It was able to detect the other buildings as well. So the reason for that, because they look very much similar. So it's basically identity based on human vision. Kind of if they're the same, they're similar, they will extract the buildings for you. And you can also use prompts. This one is even more advanced. Give an imagery, I want to extract the trees. Just type trees. It will extract the trees for you. So I want the buildings, you will extract the buildings for you. We're not using this one for this. We can probably try, but I'm not sure if it works or not. Again, the model itself is not trained on geospatial data, but it's the kind of the transferability is pretty amazing. Just like ChatGPT, if you use it, you know how powerful it is. It can answer all kind of questions, coding, whatever you like. So let me go back to this one. Okay, perfect. Now it's done. No error. That we are good. So we can show the mask. Okay, take a look. So now we have a lot more details of the boundary. And similarly, you can just show the annotation. The annotation basically showing the mask on top of the original imagery. So look at this one. Can you identify any missing trees? Probably there's still some, but it's so much better now, right? So it looks so much better. And again, you can compare the data. side by side. Okay. I think even better is that I can maybe copy this code block so we can add the data on the interactive map so we can actually visualize that. So let me copy this code block here, and I'm just going to add it here in a new code block, paste. So for this one right now, we are adding annotation 2 here. Oh, I think it's mask 2, whatever. Oh, let me see here. Yeah, mask 2 as well. So the mask is just the gray scale color. So let me add this one, mask 2. I really don't need the Google-based map, and so we can compare the result right now compared to the previous one. Right? Pretty good, right? Not bad. Of course, you will see some of this. We can remove it later once we convert it to vector data, but just simply based on the visualization, it looks pretty decent. Right. So this is the power of using this kind of a foundation model, is that you don't need to be a machine learning expert. You can use the foundation model and then just create a result and then just get access to. So this is just the raster data, basically the mask, and all the data are being downloaded on the left side here. So if you need, you can actually click the button here. You can download this one to a computer, and then you can open using desktop.js. So for example, once you're done, you can save this one to Google Drive, or you can just download it. And for example, I also want to download this mask, download it, and then you can just open using QGIS to visualize data locally. You can do some further data analysis. So I'm going to open this one, and I'm going to add maybe just the Google-based map here, and let me drag the data. So this one is only 2.3 megabytes, so it's pretty small file. And now I can zoom to this area. Right, this is the mask. This is the area. Right. Of course, there's some artifacts. I will show you how to actually do some fine tuning. So, and this is what you get. So you can easily segment the trees. If I don't need to speak here, probably takes you 2 to 3 minutes. You run automatic. If you have a new imagery, you just change the input file, you run again, you get the result, right? So you can automate the whole process to delineate this, do the segmentation for all kind of areas.
And you can also program to push this data set back to GitHub as well.
Mm-hmm.
You have know how to do it.
Okay, so this is how you oops. Yeah, it's Google Colab is a little bit buggy. If you run it, if you have a GPU on a local computer and a server, this is a lot more smooth. So it runs so much more smooth. You can see the imagery very, very quickly. But I don't have a GPU on my laptop, so I cannot really showcase the effect. So this is how you get the result. I think the last night I implement another functionality that you can convert this one to vector data. You can remove some of those objects that you don't want. You can also specify the minimum and the maximum. Basically, when you are saving the mask, by default it's saving all the masks, but you can actually fine tune it. So I can show you the result here. And I haven't tested on this data set, so I'm not sure if it works or not, but I can show you the result, what it looks like. So I literally just finished it last night. Right, so you can get all the, for example, extract all the buildings, and you can see, you can calculate all the attributes, the area, the size, the volume, the orientation, the extent. We can try it here on live. Yes?
I have a question. Maybe I missed from your explanation. What if instead of an RGB, you have a multispectral ortho image? I mean,
I will just use the RGB.
you will work in the same way? I mean, would be able to segment the different instances?
Yeah, right now it doesn't support more than 3 bands yet, because the foundation model was trained on just RGB photos.
Okay, but what if you put with a free band with a near infrared radiation?
Yeah, it works as well. It's just 3 bands. It doesn't matter if it's what RGB band or it's near infrared. Just give me 3 bands, whatever band you like. But right now, it only supports integer 8, so 0 to 255. If you're using the floating point, you might need to rescale it.
Okay.
But I think I'm thinking about adding the support for floating point, so you don't have to do the conversion yourself. So you can input any data you like. And if you only have 1 band, you can also just copy them another 2 bands. So basically, the input is 3 bands. What information it is, it doesn't matter. So behind the scenes is just seeing the pattern. So kind of like you are using desktop.js, you can change whatever band combination, right? And so if it shows some patterns, if human can see it, the model pretty much can extract that. So it's kind of based on similarity. Yes?
So did I hear you say you could even maybe like count everything above a certain size, like if you
Yes.
said the minimum and
Yes.
maximum?
So let me show you. This is what I'm going to do. Again, I haven't tested on this data set. I just finished it yesterday. So I'm not sure if it works or not. But the example here that I'm showing you here, you can calculate, for example, the area, the bounding box, orientation. You can also see basically the geometry, all kind of attribute. So let's try to see if it works. Let me go back to here. There's a function. I forgot what I did. Yeah, region groups. So basically, we're going to do some data processing on this data set. So what we are generating here is this one, right? The mass 2. And this is the one that we're seeing here. So right now, we are trying to do some analysis on this one, trying to extract how many objects in here. Do we remove some small objects, fill some holes, and you can remove some large objects, and then we basically get a much better result. So in that way, you can count how many trees in this area, what's the average size or something like that. You can do some calculation. Because you see, it's not perfect, right? You see lots of those like artifacts. It's not really artifact, it's what the data, the model generated. So what I can do here is create a new code block, and then what should I be doing? Let me look at the source code again, region groups. So actually I have a function here, SAM02 region groups, SAM02, and so there's a function here, SAM2.region groups, and then I can provide the data. So what you can do here, if you want to try it out, all right, this is the model that we have, SAM2.region group. Okay, it pops up, so that means this is the latest version that we have right now. And then I can parentheses, so the imagery, so we're going to pass in this mass 2 imagery, and inside here you can have the connectivity. Basically, when you're trying to do the region groups, you can have like 4 connectivity, or you can have 8, right? So when diagonal. So for this example, we just use 8, and you can set the minimum size. For example, this is 10 pixels. So for example, if you want to remove smaller area, like less than 100 pixel, but no more than 2,000 or something like it, you can specify. So, and also there's one here called threshold. For example, there may be some object that have some small holes inside. You can fill the holes as well. So what we can do here is that, okay, mass 2 .tif, and then we're going to set the mean size, for example, equal to, let's say, 10 pixels. If it's less than 10 pixels, I'm going to remove it. And also, I'm going to set the max size. So if you know, for example, in this case, in your area, all the object that you're going to extract is pretty much small. If there's some large background object, you can remove it. For example, if it is more than 1,000, probably it's an artifact. You don't want it. And also, you can set a threshold to fill the holes in the object. By default, if you don't specify, it's using this minimum size. So in this case, it is smaller than, if you have a large object, you have 10 pixels inside, and you want to fill that hole with the surrounding. So after that, you can also export the output as a CSV. You can export the output image. You can also export the output vector data. So this is what we're going to do here. I can just say out imagery equal to maybe, yeah, this is a little bit hard to see, but let me do it like this. Again, there's no guarantee that this will work because I haven't tested it. So our imagery equal to maybe mass, this is 3.tif. Oops. And then I'm also going to output the CSV. So the CSV is basically calculating all the information for each object. So I'm going to say objects.csv. CSV. I can also output as a vector data. So out vector equal to maybe objects doc GPKG. So I'm going to use the geo package format. And what else? You can also specify this one out. So one is maybe the DA data set and also the GDF. So you can return the result if you need to. Right now you can save the result to your computer, but you can also pass the information back to your program. So again, let's try it. Please. Okay, perfect. So it works. That's nice. So you see it saves all the output in here, like mass, GPKG, and also mass 2. You can load this data back to the map, but I'm just going to download it just to show you the differences. So I'm going to download this one to my computer, and also the mass GPKG, and also, not the mass, it's actually object GPKG. So download this one here. Again, you can load it on the notebook, but it's not very smooth because GitHub, the Google Colab is not super smooth right now. So, right, I have all this, and at least right now, for example, I can open my CSV, see what it looks like. Hopefully it has all the information. So you see here all the label. So the label basically the individual objects, and it's better to open this one in QGIS. So you see the differences. Objects, where is it? This should be a raster data set. So, mass 3. Okay, yeah, I should name it as object. So mass 3. Mass 2. See that? See the differences? The mass 3. This is the one that's reprocessed, removing the small object less than 10 pixels, and also filling the holes. And this is the original one. So take a look at this. So basically, I remove all the pixels. And so let's look at the vector data. So it's actually better. And now this is what is actually the final outcome. So it depends on how you filter the data set. And the nice thing about this, you can click on any object. You should get all the information. So there are how many pixels, the area, the bounding boxes, and the axis, the measure length. So basically, you feed a kind of an ellipse on the object. So you can also calculate, for example, the elongation, something like that. And this one is useful because, as I mentioned earlier, right? If you see some of the things like this, probably this one is not a tree. So because the elongation is like much longer, so basically the length and the width, you can do the filtering. I can remove it. So for example, I can open this attribute table, and so all I need to do maybe depends on what attribute you're going to use. For example, I can look at the area, right? Oh, let's do some like 1 pixel. This is probably just outlier. So because earlier we set from 10 to 1,000, right? So you see most of those roughly from 1 pixel. Oh no, here the area ranging from 1 to 995 because within 10 to 1,000. And if you think, for example, these large objects, they are just not trees. Depends on which one you're working on. This looks like trees, but if you like working on buildings, other detection, if it's too big, you can delete it. And similarly, right, I can filter the data set. So let me clear this one. And this is how you can refine the data set to, for example, elongation here. If it is 1, that means mostly they are pretty much square. So they are the good results. But if it is like very elongated, probably it's not good. So I can come here and I can select maybe this one. We can take a look, right? Oops, this one. You can zoom it. Yeah, you see this one, right? Just the very elongated one. I can delete it. So if it's just a vector data, I can look at the other one. Right? So basically, you can filter. Basically, you get all the attributes. You can filter based on the size, based on the extent, or you can filter based on the eccentricity. So there are a couple of those parameters that allow you to do that. And I'm trying to add another one is that you can actually add I can add the canopy height model into the information into this attribute table. So you know the average height of each polygon. So in that way, if it's like on the ground, then you just remove it. If there's a tree, then you can keep it, right? So there will be more information being added to the attribute table. So you can watch out for the next release. But clearly, right, these are the things that it's definitely not trees. I can just select here, for example, of this. Probably anything greater than 5 or 6, those are probably not right. So take a look at this. some of this in the corner here, artifacts, and you can just edit the data, and you can just come here, select them, and you can just delete. Oops. And you can cut them, for example. Okay, they're gone. And I can cut a few more. Right, see? These are gone. And this one is also probably not right. I can also just remove it. Where is it? Cut it. Anyway, those are some like basic GIS editing, so it's up to you how you want to do it. But now you can see we give an imagery, we delineate all the trees, we calculate all kind of attributes, size, area, and now you can actually have an idea about how many trees in this area, how big are they, and later when we add the DM, the CHM, you can see how high are they. So what's the volume, that kind of information. So there are a lot of things you can do, and as you can see, it's pretty straightforward. A couple lines of code, and then you can get all the information. And then this is the one that you can use it to add more information attached to each polygon. For example, when it was like irrigated, how much like fertilizer you put into that, something like that. So you can actually build kind of like inventory. And this is kind of like right now I'm taking a photo, I extract each of you, I attach some information to each of you. Kind of like in the government, the system, they contain information for each of you. But right now we are doing it for just for agriculture, for trees, for whatever you like. Questions? And okay, so we still have a little bit more time. So the next one here I'm going to show you is using a bounding box. So this is even better. So if you already have some bounding boxes, it can do a much better job of delineating all the objects. So we're going to use this bounding box from the D2S. So this is the one on the platform in here. So we go to the D2S platform, right? So this is the tree boundary, and it's nice that we already have the tree boundary, but it's not so nice because it's a rectangle. It's not really a refined boundary of each tree. So what we are doing here is to use this one as an input into the model. So right now you see here we have loading it on the map in here. So what we're trying to do is that we want to ask the model to delineate the object based on the bounding box. So it's going to give use the bounding box as kind of a guide, and then just going to refine the boundary. And so for this one, we're going to do the same thing. This one right now is only supported for the segment NEC model version 1. I'm trying to implement version 2, but it's not finished yet. So the version 1, the model actually is a little bit larger, so it's 2.56 gigabyte. But it should work in this case. I think we should have enough GPU to do it. When it's loading the model, it will clear the previous one. So hopefully it will work. And you can see the result in here. This one is basically giving based on the so-called box prompt. Basically, you already draw the rough outline of the tree, and then you tell the model, okay, extract the object within this bounding box. And the nice thing about this, when you see overlay on top of it, right, it's actually not perfectly within the bounding box. When it does the extraction, it can go around the object. So it doesn't need to know the perfect location. You just tell me roughly, okay, the object is within this bounding box, it will extract that for you. And because you have so many bounding boxes, it's going to extract all the boxes for you. All right, so it's done, it's loaded. Then we can set the imagery, and then you can do the prediction. So right now, so earlier we used the drain rate. The drain rate is basically automatic segmentation. The predict this is kind of like supervised classification, because I give you the bounding boxes. I already know roughly like where it is, and you tell me the exact location. Kind of like you are trying to find someone. Like right now, I take a photo. Each of you, I roughly draw a rectangle, but I don't know the detailed boundary. You will be able to do that. So just use the predict function, and you can pass in the file. So we are passing the GeoJSON. So this bounding box is a GeoJSON. So you can, if you already, okay, too bad, out of memory. So you might need to restart it, but it's fine. I can just show the result in here, so you can see it's so much better. So you can refine the boundary, and at the end, you're going to get something similar like this. So it's going to give you a raster file, and also going to give you can convert the raster to vector, and then can calculate all the geometries. So in that way, you know exactly how many trees within your area, what's the height, that kind of information. So to try it out, it doesn't have to be this area. It can be any remote sensing imagery. So it can be buildings, okay? So it can be vehicles, it can be airplanes, it can be anything. So it can be generalized to do all kind of detection. So try with your own data. Again, try with a small data set first. If it is too big, you're going to see this GPU because it's pretty computationally intensive. If you don't have a GPU, you can also run it using the CPU, but in general, it's 10 to 20 times slower. So if this one takes 2 minutes to do, using the CPU probably takes 20 minutes. It can still be done, but it's just not fast because GPU is very suitable for this kind of task, doing this kind of parallel processing, doing the image processing. So I don't want to restart everything from scratch, but once you get the tree mass, then you will get something like this. Yes?
When you run out of that GPU and you have to restart, do you lose all of the work that you've done before? It says up at the top.
Yeah, you need to rerun the code again. So for example, here I need to just say restart section, and what you can do here is to, let me show you. You can just go to, all you need is just a couple lines, or you'll be doing like something here. But the annoying thing is that because we're getting data we still have the data, so we don't need to get the data from D2S. So I can actually go directly to here. I can go directly to the second one here using the bounding box. And yeah, the tree boundary, you need to basically rerun some of the code block. Because you're defining those variable, if the variable doesn't exist, you're going to run into error. So right now, if I run this one, probably doesn't work because it said the tree boundary is not defined. So I can, did it download it here? Yeah, it's here. So we can actually do it directly from here. So I can say tree boundaries, and then .geo.json. Okay, it works. And then now I can load this one. Anyway, so you need to load the imagery. So you basically need to add the imagery. The imagery is equal to, you just run all the previous code block, it should work. But don't run the segmentation model too, because they want to use the GPU. So run anything don't use the GPU and run again, then it should work. So maybe I can show you here. Segmentation model 2. Anyway, I think I will just skip it. You get the idea. So try it again, and then run the couple again. You should be able to see the result. So this is kind of just the snapshot of the result. And the idea is that take any set of imagery, Jung imagery, put into the model, do the segmentation, and then get some result, and after you can fine tuning. So it's not going to be perfect. You will need to actually to remove some of the artifacts, remove some of the things that you don't want, and then kind of get a refined result of the segmentation. But if you need some like very interactive way, then you can check out the something like this. Like I showing here, I also have a lot of YouTube video here showing you how to do that step by step. So you can run it. We don't have time to do all that because the GPU limitation. But if you have a large GPU, you have access to a server, then you can try this one on a much larger data set. But what we want is to introduce to some of these tools that it's freely available, it's open source, open access, you can try it on anything. So what I'm doing is like, okay, I built a ChatGPT, I provide you for free, you don't need to pay OpenAI $20 per month to do that. Now, you can try out some of these things, see how it works, and then if you really like it, then you can start buying some server with a GPU to run on things on scale. Okay, any questions?
So instead of taking a break, why don't we just go ahead and finish 30 minutes always?
Okay, so for the
part 2.
Yeah, for the part 2, I'm going to go through very quickly. If you already have a Google Sensing account, you can try. If you don't worry, you can sign up later. because we don't have time to go through all the detailed ones. So you can access a notebook here. Let me quickly show all, because there are some things I want to show you that might be useful for your applications. So this is section 2. So if you click this one here, it will take you to the Gmail website, and you can do the same thing here. You can open this one in Google Colab. You can install the package. You can run it on your computer. So you can also download this one to your local computer. So I'm going to try this one here, and I'm using my local Jupyter Lab. Like I said, it's a lot more smooth. The visualization is so much better. So I'm going to contact activate. Maybe. I just want to show you the output, so you can always come back to see the detailed source code. So let me zoom in a little bit. And this one is using Google Sensing. So the first section, we're actually doing something very much similar. We are connecting to D2S, getting the data, and then getting the bounding boxes. But later, we're going to combine with satellite data. So there are a lot of satellite data not available on D2S, but it's available from the cloud computing platform. How do we get those data to combine data from multiple sources? Then you can run some data analysis. So I'm going to run this one, and this is still using leaf map, so it's very much similar to what we did earlier. And I'm going to skip this and directly go to the D2S. So this is the same one that we just did earlier. I'm going to change this one to my account. Oops. Oh, probably it's on. I think it's on the other one. Sorry. Let me show here. Contact activate. Same. Hopefully this one works. So let me try again. Oops. Interesting. Maybe Geo. D2S. What? 1 second, let me reboot. Okay, it works now. So let me skip to this section. Oh, sorry, not this. Yeah, change this one to your own username and password, then hopefully it works. Okay. All right. So at the endpoint, and so for this one we're using the second project. So this is the which one? The Config. Yeah. So I'm going to show you the data product. So the process is exactly the same. And so I'm going to show you what it looks like here. So this is from June 2023. Right, so this is the imagery. Again, you should have access to this one on the D2S platform. And so this is the very high resolution imagery, the Jung imagery. You can see here each row. And so what we're trying to do here is we're going to overlay this project boundary and also the grid boundary. So basically, you see earlier using the D2S. So what we're trying to do here is we have this Jung imagery, and we're trying to monitor, for example, the growth of within each grid and each plot, for example. And we can utilize some satellite data to calculate basically the trend, how it's like growing. And so in this case, we can use the Google Sensing. So Google Sensing, if you have never used it, is a cloud computing platform that allows you to access a tons of satellite data in the cloud, and it's free for research and education. It's very powerful. It's kind of like YouTube. you watch all kind of video, it's free. But here you can access all kind of geospatial data. And so let me show you here. I don't know why it's a little bit slow today. Do I have an internet problem? Okay. So sometimes you ask you to re-authenticate, so let me do it very quickly. So this is kind of log into your Google account. Oops. Caller doesn't have to. Okay. 1 second. Yeah, sometimes I have different accounts, so it's kind of annoying. Let me restart here, this section. Yeah, because there are multiple accounts, multiple browsers, so sometimes you just get confused about which one to use. And ebooks. Run or restart from all selected above. Okay.
I mean, Qiusheng is doing a lot of things very quickly, but
Don't worry, you can watch later, but you have to basically just one step by step. You will not see so many errors today. I'm running it because of the account, different account. But if you're just using one account, you should be fine. And so let me show you here. So right now, yeah, this is working now. Google Sending. You can see the map in here. And so let's rerun this one. So now we can see the data. So this is basically using Google Sending data, and I can feel the get the boundary, visualize the grid. So look at this one. So right now we're using Gmap. So this is a different Python package. So we are getting the grid boundary from D2S, and we're loading here. So next step is to actually retrieve the data from Google Sending. So we have a lot of satellite images from Google Sending. So what we can do here, the first one is accessing, for example, the USDA name imagery. So this is just for the US, and this is high resolution area imagery every 2 to 3 years covering the entire US. And you can actually get the data for any area that you're interested in. So right now, look at this. I just create a time series for this cornfield, and we have data at the lower right corner here, starting from 2003 up to right now. And you can zoom in. You can change the slider from 2005, 2007, 16, 2020. You can see the changes, so you can see the time series images available for any location around the US. And you can see the changes. Of course, we have the Jung imagery, but the Jung imagery is limited. You only have a couple time periods. For satellite imagery, for USDA, it's the same thing every 2 to 3 years. But the nice thing about this is you can actually access Sentinel-2 imagery. For example, I am going to get, because the Jung imagery was required in 2023, right? So I can actually access satellite data. I can specify data from January 1st to December 31st. So basically, I want to look at all the Sentinel-2 satellite imagery covering this area. And I also want to select cloud cover less than 1%. There are tons of data covering this area. So if you go to, for example, 90%, you get a lot more images, 332 images. So you don't have to go online to download the data. So what we're doing here is telling Google Sending, okay, give me all the data with cloud coverage less than 1% for my study area. And I want to select B2, 3, 4, and also B8. So basically RGB and also near infrared band. And then I'm going to convert it from basically integer to floating point. And I'm just going to clip to this area. That's it. And so right now we have 73 images available for my particular plot. And so you can look at all the dates. Right. So basically the Jung imagery is, what's the date again? I forgot, like only particular day in 2023, we only have one time period. But right now using a satellite, we have 73 images for this time period, for 2023. You can see all the dates in here. And then we can calculate the NDVI. So calculate NDVI means for every imagery, we can calculate NDVI. So we have 73 NDVI for this particular plot. And now we can actually take a look at the Sentinel-2 time series. So this one might take a couple seconds. So what it's doing is going to the cloud, to the server, to get all the data and running all the computation. And now we have 31 images. Because some of the dates kind of like duplicate, because you might have 2 images that it doesn't cover the entire plot. So you might have 2 images with the same date, and they're going to do the mosaicing. And after that, so now we have all the images in here. Each one has 4 bands. And it's probably easier just to visualize them on the map so you can see the details. And so I wanted to click here. We don't have to go into the details, but what we're doing is we're just going to add the time slider to the map so you can see all the Sentinel-2 time series images covering this particular plot, and then you can see the visualization. So you can basically you can get all kind of data from different satellites. It can be Landsat, it can be Sentinel, it can be anything. So if you're interested in learning more, go to the Google Sensing data catalog here. Where is it? Google Sensing, and then go to the data set. It has right now over 100 petabytes. 100 petabytes, so it's 100,000 terabyte of data. It's a huge data catalog, so all the data are freely accessible. And you can try it out. And so look at this. Wait, here. So right now for this one, this is, we are right now visualizing the Sentinel-2 data. So I can turn this one off, and I can take a look at the time series. So here, this one right now is, we are looking at January 1st. It might take some time to load up, depends on the internet speed. So we are retrieving the data on the fly from the cloud, and throughout the season, you probably see different the changes. So the nice thing about this, we don't have to go online to download the data. We are getting the data on the fly, and then ask it to render it. And this is exactly the same, just like you're watching any TV shows. Nowadays you don't buy DVD, right? You don't buy Blu-ray. Just go to Netflix, like, okay, Game of Thrones, season 1, season 2, season 8, something like that. You generally just watch it. So what we're doing here, we are looking at all the Sentinel-2 images for 2023, and we just rendered it here. And even better, you can run computation. So for example here, we can see all the grid boundary, basically each bounding boxes for each plot, and we can start running the computation. So we can actually calculate the NDVI, basically based on, for each imagery you have 4 bands, right? So you can calculate NDVI for each imagery. Then we ended up with the NDVI time series. So the last one, this is really the power of using cloud computing, is we can run statistics. So give me whatever polygon that you have, and I can calculate, for example, the mean NDVI, the maximum, minimum, something like that. And it's going to take basically maybe a couple seconds or a minute or 2. But behind the scene is processing all the time series. So we have 31 images. It's analyzing these 31 images and then getting you the output. So take a look. We have the result in here. And now I can actually visualize the data. So let me quickly show you here. This is the plot boundary, right? So I have 31 time images. So now if I hover my mouse, do you see the result being shown in here? Right? Each different date, this is the average NDVI that was just calculated using the cloud. And we don't have to run things locally. So you can see the average NDVI for each plot. You see it's changing. So we're getting those 31 images throughout 2023. And if you really want to plot it out, you can do that as well. We can also calculate the aggregated NDVI. For example, for this entire bigger area, you can calculate the roughly mean NDVI. So this is what it looks like. So for this entire cornfield, not the grid one, but the entire one. You can see the average NDVI changes throughout the year in 2023. So you can see when it's started growing, when is the peak NDVI, when it's going down, when is the harvesting season. So you can actually monitor everything like this, and this allows you to zoom in and zoom out, right, and plot. And the last one I will show you is actually we can look at individual one. So just like this one here, this map, right, each plot has a line, right? You can plot all the lines together, so you can also see similar pattern. So some of these, for example, you are doing like irrigation or putting the fertilizer on that, and not every grid has the same performance, right? So you can actually monitor the differences, see which one is performing better in terms of the NDVI. So at the end, you will look like this, right? So you can clearly see overall, every plot, it looks pretty much similar, but certainly there's some changes at the end here that are a little bit different, right? Some like decrease, there might be some disease or other stuff. Some are pretty good, right? So overall, you can see the trend. So this is something you can do using cloud computing to combine data from either locally, or you can combine data from cloud, from satellite, from area imagery. You can also like run zonal statistics on the height. So if you have the canopy height model, you can also plot things, something to that. And you can see all the entire time series. So you can see the trajectory of each agricultural plot and see how it's performing, depends on how much fertilizer or irrigation or water that you put into that. And yeah, we don't have time to go into all the details, but you have access to the notebook. You can reproduce it later, and you can change it to your own data. You can change it to a different area. In terms of Sentinel, this is global scale, so you can do it for anywhere you like. All you need to just change the bounding box to your area, and then you can run it. You can get the same result just like what I'm seeing in here. And it doesn't have to be just cornfield. It can be any vegetation. It can be doing forest. You can even do water, wetland, all kind of stuff. So it's very, very powerful. And if you have any question, feel free to reach out to us. This is probably like we can spend the whole day for the entire workshop, but we only have 3 hours, something like that. So anyway, so just to introduce something that you may not know or you may not have used, and just keep that in mind next time if you're doing something, analyzing some data, you remember, oh, I remember someone saw something like this, and then you go to the notebook example. You just run it, customize your code, change it to your area, change it to your own data. The workflow read pretty much similar. And if you really want to learn Google sensing, for example, I have you can go to the GMAP website. I also publish a book. It's open access, so you can go through how to learn using Google sensing to cloud computing. So this is entire book that I can teach for a whole week workshop, but we only spend 1 hour maybe half an hour going through some easy one. But there are lots of things you can do using these free cloud computing platforms to do large-scale geospatial analysis. And right now we're only doing a tiny one. You can do it at the global. You can analyze global vegetation, global water, global forest. There are tons of things you can do using this kind of platform. Okay, so that's all we have. And any questions?
You can give a round of applause for the police.
Thank you.
And, one message is that we are hoping you get out of this.